Okay, now I let that video go just a little bit too long because for some reason I'm finding that my videos, no matter how long they go, only upload, whether to YouTube or because of something in Windows, to 33 minutes. And this one went over 36 minutes. So let me go back and just restate a couple of these things, okay, and just give you a summary of what I've said here, okay? And it bears repeating because it's really important. It's really neat stuff. Okay, so if you have a function of two variables, and it could be 3 variables, it could be 12 variables, you can do the gradient. The gradient gives you a vector field. Okay, this vector field, which could be sketched. The gradient is what we call a conservative vector field, and that's true for any differentiable function f. Okay, f is called the potential function for the field. So you have potential function, you have vector field, connected by the fact, of course, that this is the gradient of this. You have the fundamental theorem of path integrals, that if you integrate the gradient over a path C, the result is just equal to the value of the function at B minus the value at A. And there's a clear connection, a clear analogy between the fundamental theorem of calculus, where you integrate a function over an interval of a single axis, and you get the antiderivative evaluated at the endpoints and subtracted. So it should be clear how this could be regarded as an antiderivative of this, and this is clearly, in some sense, a derivative of this because everything is calculated by taking derivatives. Now, it goes deeper than that, but that's a good way to understand it when you first see it. Okay, so we have this, and of course, I've said it already, C is the path, the integral is a line integral, A and B are the endpoints of C. Okay, now we have the equivalence statement, and this is where the video might have cut off. The equivalence statement that the integral around a closed path of the gradient is 0. Again, given restrictions on the differentiability of the functions and integrability and stuff that you can understand pretty easily if you understand the concepts. And then hopefully you can make some progress in being able to prove these things. Okay, so for any closed, this is true for any closed path C. Okay, as long as C is a closed path, that means the endpoint is the same as the starting point. There you have it. Now, you have no idea how important integrals over paths are, especially when you get into functions of complex variables, and you might, depending on the path you take through your engineering or whatever STEM discipline you end up with. So I can't overemphasize the importance of this stuff. For any closed path C, then this integral has to be 0. Why is that? Well, because the endpoint is the same as the starting point in a closed path that ends where it started. That's what closed means. And if the endpoint's the same as the starting point, then this is the same as this because B is the same as A. And you're subtracting these, you're going to get 0. So it's very clear that this follows from this. Okay. You can also conclude this from this. If you have an integral from A to B, and the integral over any closed path is 0, then, and this is actually a little better than what I said last time anyway, then you could complete a path from B back to A, and the integral around this whole thing would be, well, that would be the integral over a closed curve. If I take another path here, you say the same thing. So no matter how I close the curve from A to B to return to A, the integral from here to here is equal and opposite to the integral from here to here. Because if we assume that the integral over any closed path is 0, whatever the integral is from here to here, the integral from here back to here has to be its negative. okay? Which says that it doesn't matter how I get from A to B. If I take alternative paths from A to B, and that's the way I should have drawn it, then any path from B back to A is going to give us 0. Doesn't matter what path this is, you put all that together and you conclude that you get that the integral is path independent. Okay, not a hard thing to understand once you ponder it for a little while. Okay, now one important thing you need to be able to do with conservative vector fields is determine if they're conservative. Still having a problem here, Alan? Okay, there we go. Okay, so if del F is conservative, del F this would go better if I started out with a good statement. Okay. Okay, if f of xy is conservative, then f equals del f for some potential function f of xy. Okay? If f equals del f, which is fxi plus fyj, then again, notation. Got to say that a little differently if I'm going to go where I want to go. Sorry. If f of xy equals, say, m of xyi plus n of xyj, then m equals fx and n equals fy. Why is this? Because f equals mi plus nj equals del f, which is fxi plus fyj. The I components have to be equal, the j components have to be equal, so m and n have to be fx and fy. M has to equal fx, n has to equal fy. So M y equals f x y, and nx equals f y x. Okay, m equals fx, so my is fxy. N equals fy, so nx equals fyx. Thus, my equals nx. This is your test for whether you have a conservative field. That's a big deal. There's your test. Now, if you have a conservative field, then you should be able to integrate these to integrate m and n to recover your gradient, or your potential function. So fx equals m. So f is some integral of m with respect to x. Fy equals n. So f also equals an integral of n with respect to y. So all you have to do is integrate m and integrate n and see that they give you the same function f, or that they can give you the same function f. That some integral of m dx equals f, some integral of n dy equals f. When I say some integral, you have integration constants. Okay? The integral of m with respect to x might not actually give you the potential function. The integral of n with respect to y might not give you the potential function, but this integral has a constant, an integration constant, and since you're integrating with respect to x, that integration constant could be any function of y. And when you integrate n with respect to y, x is constant with respect to y, so your integration constant can be any function n of x. Let's see how that plays out. Now we already know, no actually we don't, I haven't told you what the potential function is. Matter of fact, I haven't even specified a function. So let's go back to the function we had here and see how it works out. Let's pretend that we know this, but we don't know this. But we now know that we have a way of finding this if we know this. Okay? Example then. If f equals 2xy cubed I plus 3x squared y squared plus 3j, what is f such that the gradient of f equals f, big F. Okay, well, using our m and our n, first of all, my equals 2xy cubed partial of 2xy cubed with respect to y, which is 6xy squared. And nx equals the partial of 3x squared y squared plus 3 with respect to y, and that's very easily calculated. That turns out to be by darn 6xy squared. So f is conservative. Now, if we didn't already know this from the fact that, our vector field f equal to this is the gradient of this thing, we would have discovered at least that there is some function f of which this is a gradient. And then we find the function, and the method is always the same, but of course the execution depends on the nature of the functions. We want to find f. How do we find f? Well, f is an integral of m with respect to x, which is an integral of 2x y cubed with respect to x. Well, antiderivative of 2x y cubed is x squared y cubed, and that matches what we know to have been the potential function that we pretend we didn't know in the first place. We've already discovered this much about the potential function. Okay, but we don't have the 3y, so we better panic. Or, remember that we're integrating with respect to x, so that any function of y doesn't change the fact that this is an antiderivative of this. Because if we take the derivative of this with respect to x, we should get this, and we do. Derivative of this clearly is 2xy cubed, and the derivative of g of y with respect to x is 0. So, nowhere to go. Okay? That's no problem, so we know that we could add any function of y, which is going to allow us to add our 3y. But to find out that we got to add 3y, we'd better go ahead and say that f is the integral of n with respect to y. And n is 3x squared y squared, not cubed, plus 3. And our antiderivative is, again, x squared y cubed. Because, antiderivative of y squared is y cubed over 3. Takes care of the 3, and we get an x squared y cubed. Then plus integral of 3 with respect to y, which is just 3y. And then plus some function which we'll call h of x. Turns out we're not going to need an h of x, but we could. Had I added another x term independent of y, we would have needed the h of x. So if this thing had had an x term, kind of like it has the 3y term that you don't see in this integral, you have to be careful about that. So, f equals x squared y cubed plus g of y, and that equals x squared y cubed plus 3y plus h of x. If I take just this much, we see that g of y equals three y plus h of x, Well, it follows then that g of y has to equal 3y. And since you don't have any x function over here, h of x equals 0. Thus, your function f is not 3, x squared y cubed plus 3y. Okay, h of x is 0, so there it is. G of y is got to be the 3y to make this equal to this, but it works out, and we've recovered our potential function. Now we have integration constants. G of y could include an arbitrary constant. H of x could include an arbitrary constant. Those arbitrary constants would turn out to have to be equal, but who needs them? If you have an arbitrary constant in here, it's constant, and it's not going to appear when you do the gradient. So why include it? You know, don't bother with it. Okay, well, that's how you recover your potential function from a conservative function. And the method is always the same. Now the execution, as I say, can get hairy. You can get difficult integrals. It can be difficult to do the reconciliation if you're not real clear on what's going on. But in principle, it's pretty simple, and usually it turns out to be pretty simple. And if you can do it when it's simple, then if you have the analytic skills or the algebraic skills or whatever, anything is simple. Okay.